Math 2414, Taylor and Maclaurin series, video 5, using Taylor's formula to show convergence. At the end of the previous video, I mentioned that it went on a lot longer than I expected, so I would pause and do another video for an example, but I forgot to look at my list of topics per video and realized something when I did. In the last video, I accidentally did 2 of my topics in one video, which is why the video was so long. So the bad news is the video was longer than I expected. The good news is we have one less video now. All right, so let me quickly summarize what we were saying in that video. We were looking at what were called Taylor polynomials, which is basically just saying, let's take our Taylor series and stop it, and stop it at some number of terms. For the 0th polynomial, we have 1 term right there. For the first polynomial, we have 2 terms. For the second polynomial, we have 3 terms. But the number of the polynomial correlates to the degree. So it makes sense we have to go out 1 more because we have to compensate for the constant in front. The third polynomial goes out 4 terms, et cetera, et cetera. We also said that we defined, we defined the Taylor polynomial by simply saying stop the series. And then we defined the remainder by saying take our original function and subtract a Taylor polynomial. Then we had Taylor's theorem that said the series will converge. The series converges to the function if and only if the limit of the remainder is 0. And then we talked about Taylor's formula that said, by the way, there's a formula for the remainder. The remainder is equal to that for some z between the center and whatever x we're looking at that moment in time. It is worth mentioning that the remainder is basically equal to the next term in the series. Because remember, the nth polynomial stops with the power of n, and if you'll notice, this goes to a power of n plus 1. So it goes to the next term in the series, but it's not the next term in the series because that would have an a there. It's basically saying this, hey, if you chop off your polynomial at some point as an approximation to this, there will be a discrepancy between the two. However, that discrepancy will be equal to the next term if you put in some other value, and that value is between a and x. Now here's where I have to be careful. This x could be less than a. So the relationship could look like this. Both of those say z is between x and a, and that's what it's what Taylor's formula says, that the difference between what we're approximating and what we're approximating it with is equal to the next term for some number between x and whatever the center is. And we can use that to show convergence because we can now set up an expression for the remainder, take its limit, and show it's equal to 0. So let's do precisely that. We are going to show the Taylor series for e to the x converges to e to the x. And in order to do that, we have to come up with an expression for the remainder and show that that expression goes to 0. All right, so what would that expression look like? Well, in general, the remainder for the nth Taylor polynomial is equal to the next term in the series, so the n plus first derivative, but evaluated at some value of z over n plus 1 factorial times x minus a to the n plus 1 for some z between a and x. Now the problem with that is that if the center is here and our interval goes to the left and to the right, whatever its radius is, we don't know if the x is going to be greater than a or less than a. If it's greater than a, the z would live here somewhere. If it's less than a, the z would live here somewhere. But the problem is, for x's over here, the relationship is this. But for x's over here, the relationship is this. So we can't definitively say that z is bigger than x or z is less than x. We just know it's between x and a. To resolve this, we're going to do one of 2 cases. But first, let's talk about what this means specifically for e to the x. For e to the x, our remainder looks like this. Every derivative of e to the x is e to the x. So when we evaluate it at z, we get e to the z. And our series was centered at 0 because it was a Maclaurin series. So instead of x minus a, it's just x. So we know that the remainder looks like that for some z between a and x, except in this case, it's for some z between 0 and x. Problem is, we don't know if x is positive or negative, so we don't know if z is less than x or z is greater than x. So we're going to look at one case. We're going to look at the case where 0 is less than z is less than x. In other words, our x is positive, and the z that makes the remainder, that gives us the remainder, is between 0 and x. If this happens, then because e to the x is an increasing function, we know 0 is less than e to the z, which is less than e to the x. Remember, e to the x looks like this. It's increasing, so the bigger a number, the bigger the e to the power is. So what does that mean about the remainder? Well, the remainder was equal to e to the z over n plus 1 factorial times x to the n plus 1. E to the z over n plus 1 factorial times x to the n plus 1. Because e to the z is less than e to the x, we've got that the remainder is less than this. But because we're considering the case where everything is positive, then everything in this expression for the remainder is also positive, including the x to the n plus 1. So we know that all that is greater than 0. What we're doing is we're setting up the squeeze theorem or the sandwich theorem, because now if we take the limit of this as n approaches infinity, there's no need to take the limit over here because it's 0 and it's not changing, but we'll put it over there for the sake of consistency. Look at the limit on the right. This e to the x is independent of n. We had to replace the e to the z with the e to the x because z does depend on the choice of x and n. So we couldn't say that z is independent of n. But on the right side, e to the x is independent of n, which means we can pull that out of the limit. And we get e to the x times the limit as n approaches infinity. Let's put the x to the n plus 1 over n plus 1 factorial. And in a previous video, we showed that this limit was 0 since the series converges. The individual term has to go to 0. So that's 0, and so that means that the limit on the right is equal to 0. Of course, the limit on the left is equal to 0. And so what we've done is sandwich this limit between 0 and 0. The squeeze theorem or the sandwich theorem says that that limit has to be 0. So therefore, the limit as n approaches infinity of the remainder, the guy in the middle, is equal to 0. Therefore, the series converges to e to the x. Sorry, I really don't want to go to another page. All right, so is it tough to show that a Taylor series converges to the function that it's approximating? Yes and no. Yes, if you've never done it before. No, if you get used to it. But the trick is to come up with an expression for the remainder in terms of the function in play, in this case in terms of e to the x, set up some sort of a limit and some sort of bounds that squeeze that limit to be 0. And since the limit of the remainder approaches 0, that means that your series converges to your function. Now, this was just case 1 where the x was positive. There technically is a case 2 where the x is negative. And so the z is between x and 0, but now the z is negative also. I challenge you to try to replicate the proof for case 1 to show that we also get convergence of the Taylor series to the function when your x is less than 0. I know what my students are thinking right now. Oh my gosh, I can't do this, or this is new and weird and I don't want to do it. I got some good news. The most of what I'm going to ask you to do is not this. This was just kind of a theoretical sideshow, if you will.